There are some topics which when you search on internet, you are bombarded with jargons and then you are lost in between jargons. Principal component analysis is one such topic. And why do you come to Unfold Data Science, guys? You come to understand things jargon free. Welcome to Unfold Data Science. My name is Aman and I am a data scientist. What I am going to do in this video is I am going to explain different pieces of a puzzle known as principal component analysis, and in the end I will combine all these pieces and tell you what is PCA and how it works and what is the internal mathematics, and I will also show you in Python how it works so that you understand this complete concept as a package. What I expect from you? Only one thing, guys: patience. You already know this is a very complex topic, and hence kindly ensure to watch till the end. This puzzle will be very easy to understand. So let me take you to the whiteboard and try to explain different pieces of this puzzle. Okay, I have written here I am going to explain many concepts in this video, because if I skip any of these then it will be difficult for you to understand PCA. Okay, so first we will understand what and why of PCA, and then we will go and do some mathematical reflex because it is necessary for you to understand PCA. Then I will give you some examples of eigenvalues and eigenvectors, which is very important to understand from PCA point of view. Most important, guys, we will do manual calculation of PCA, which means we will not use Sklearn's PCA. We will do the manual calculation and then see how it is coming out, and we will compare with Sklearn PCA, and then in the end I am going to tell you summary of our learnings and what are the limitations of PCA. Okay, so let's start, guys. Lot of things to cover without any further delay. What and why of PCA, right? So what is PCA, guys? If somebody asks you, PCA is nothing but a feature reduction technique. Feature reduction technique. Why feature reduction technique is needed? In a data set there can be many features. For example, feature 1, feature 2, up to feature 100. All these features are not equally important, you know, from your data science experience, right? So feature 2 may have same information more or less which feature 5 is having. In that case, I don't want to overload my model with redundant information. Hence I want a solution to reduce the feature. At the same time, I do not want to extract the meaningful information out from the data. So to solve this issue, there are different feature reduction techniques, and one such technique is known as PCA, standing for principal component analysis. So what PCA does? If you take your data and if you apply a principal component analysis on your data, all these features, right? What PCA will give you is, PCA will give you principal components. We will understand in detail what is principal components. For now, I am telling you, for these 100 features, PCA will give you 100 principal components. Okay. One more interview question, guys. How many principal components for 100 features? Okay. 100 principal components by default. Out of these 100 principal components, what PCA tells you is, you no need to consider all these 100 principal components for your model training. Rather, you can consider top, let's say, n features. Top n features. On the basis of what I will select top n features? On the basis of how much of my data variance is explained by these features. So how it works generally is, your PC1 will explain most percentage of your variable in your data. So 80% of your data will be explained by PC1. Another, let's say, 15% will be explained by PC2. Another 3% will be explained by PC3. And whatever is left will be explained by another principal components. So you no need to take, anything after PC3 in this case, because if you see 95 plus 93, right, 98% of your data variance is explained by first 3 components only. So from 100 features, you have come down to 3 principal components, and you are losing just 2% of information of your data, because 98% is being explained by first 3 principal components. Okay. Now it's not very simple, guys. reducing your 100 features to 3 features. It is complex mathematics behind it, and hence I have broken it into multiple pieces. We will go one by one. Fine. So first of all, guys, few basic fundamental things we will discuss. I hope you know what is the difference between a scalar quantity and a vector quantity. If not, let me give you a small examples. Anything where you see only magnitude, it is a scalar quantity, and anything where you see magnitude and direction both, it is a vector quantity. For example, if I tell you what is my weight, okay, weight does not have a direction, just a magnitude, so it is a scalar quantity. And vector quantity example, let me give you like this. Suppose there is an aeroplane flying, okay, and this is your x-axis and this is your y-axis. Now somebody asks you what is the position of the aircraft. Let's say this is 3 units on x-axis and 4 units on y-axis. Somebody asks you what is the position of the aircraft. You can say something like 3, 4, okay. This is the magnitude, but in which direction this magnitude is there? So direction you will say like this, x, y. So in x, y direction, the respective magnitudes are 3 and 4. So what we are discussing here? We are discussing here a magnitude and a direction. So this is a vector quantity. Simple. Let's move on to next mathematical concept known as matrix. So in mathematics, guys, if you write few numbers like this, right? This is a matrix. You know this already. Okay. And what is the matrix transpose, guys? If I apply a transpose on this matrix, then this will be like rows will convert into columns, columns will convert into rows. This becomes your matrix transpose. Okay. I'm sure you know matrix multiplication, but just little, detail. I will do a simple matrix multiplication. If I have to multiply this matrix A with the below matrix B, right? How the multiplication will happen is it will go like this. You have to go in first matrix row wise, second matrix column wise, okay? So the result of this matrix multiplication will be 1 gets multiplied with 3 and 2 gets multiplied with 4. This becomes one element of your multiplication matrix. Again, 3 gets multiplied by 3 and your 4 gets multiplied by 4. That is your another element in the matrix. For matrix multiplication, remember guys, the dimensions should match. So if I am considering row wise here, then row is 2. This should match number of columns here. Am I saying other way around? Number of columns here should match number of rows here. Yeah. So number of columns here 2 and number of rows here 2. So both these things should match. You already know this, just a refresher. Okay. So this is your multiplication product. Now, what I'm going to do is I'm going to tell you the concept of something known as eigenvalues and eigenvectors. Okay. So you saw one matrix, guys. Let us call that matrix as matrix A. For any matrix A, okay, understand this carefully, guys. For any matrix A, if there is a vector V such that if I multiply that vector with a scalar quantity, then this equation becomes true. Then this lambda is called eigenvalue, okay, for that matrix A, and this V is called eigenvector for this matrix A. One more time, guys. For any square matrix, if there is a vector V such that if that matrix is multiplied with this vector V, and if a scalar is multiplied with this vector V, then the results are same. Then this lambda is called eigenvalue and this vector is called eigenvector for this matrix. One example, it will be absolutely clear. Suppose there is a matrix, simple matrix, guys. I will write here 3, 6, 5, 4. Okay. And if this gets multiplied with a vector, okay, and if lambda gets multiplied with a vector. Now suppose I want to find out what are the eigenvalues and eigenvectors for this matrix, okay. So what I have to do is I have to solve a quadratic equation basically. So how it will be solved is you can just bring this this right hand side term here and equate it to 0, and if you take the V out, then you will see that inside we have our matrix, okay, and then we have our minus lambda I. I is nothing but your identity matrix, okay, is equal to 0. Assuming V is a non-zero quantity, if you solve this equation, right, you get the value of lambda first. So your matrix is what? 3654, right? And you are multiplying with lambda identity. So let me write it here. Maybe some people might not be able to get if I tell like this. Lambda into identity means your identity matrix is nothing but a matrix of 1 0 0 1. Okay, all your main diagonals will be 1, other will be 0. So if I multiply lambda with that, then what happens? Lambda 0 0 lambda, this is equal to 0. Now what is this? If you subtract two matrices, 3 minus lambda, 6, 5 minus 0, 4 minus lambda, 0. Now if you want to solve this, 3 minus lambda multiplied by 4 minus lambda minus 30 is equal to 0. Okay, and this is nothing but a quadratic equation, guys. And if I solve this quadratic equation, I am seeing in my notes, you get two values of lambda. One is 9 and other is minus 2. Now, important thing to understand here, guys. I told you the definition of eigenvalue and eigenvector. So how many lambda values I am talking here? 9 and minus 2. Two different lambda values means two different eigenvalues. So how many vectors will be here? One vector will be associated with this, one vector will be associated with this. Okay, so in the end you will have lambda 1 v1 one combination, lambda 2 v2 other combination. Now why we are doing all this calculation and why it is extremely important concept in mathematics. If you see here carefully, guys, our matrix, right, which is a 2 cross 2 matrix, we are able to represent this matrix by a vector, which means we are bringing it to a lower dimension. Okay, and lower dimensions mean nothing but dimensionality reduction. So what we are doing here is we are trying to see in which direction maximum variance is there in the data. Data means matrix in this case. So for example, if this is your vector 1, okay, so vector is what? Your direction. Remember this, guys, understand this. Your vector tells the direction, okay, and your lambda value, which is your eigenvalue, tells you what is the magnitude in that direction. So I understood the direction, but what is the magnitude? So your lambda value is, one value is 9 and one value is minus 2, right? So this is your magnitude in this direction. This is the mathematical intuition behind something known as eigenvalue and eigenvector. We are decomposing this matrix in a lower dimensional space and we are knowing in which direction how much is the magnitude. Fine. After this, what we will understand is how to compute. We have done all the raw work now. How to compute PCA step by step. Okay. So suppose, guys, I take a very simple data here. Okay. I take marks of two students. Okay. Physics, I will write here physics and I will write here maths. Okay. This is my student 1. This is my student 2. So student 1 scores some A marks, student 1 scores in maths B marks, C marks and D marks, right? I will take this simple data and I will tell you step by step how PCA is calculated when you call Sklearn PCA. First of all, what will happen is, this is step 1. Let me take a different color. This is your step 1. What you have to do is, first thing you have to do is, you have to define data, which I have done above. As you can see, I have done here definition of data. Okay. In step 2, what you have to do is, you have to make data mean centered. What is the meaning of mean centered, guys? Suppose in physics, this guy scores 10 marks, this guy scores 12 marks. Okay. So feature by feature, this is your one feature, right? This is your other feature, right? Feature by feature, we want to kind of scale the data. In this case, we are doing the mean centering based scaling. Okay. That is the step 2. And now I will tell you one step and take you to the Python notebook also. So guys, if you can see here, let me go to my Jupyter notebook. Okay. As you can see here, import numpy pandas matplotlib, and from numpy.linear algebra I am importing eigen. So I will tell you what it does. Like the way I was saying you, I have defined a marks data here, and these are the marks of the students, okay, in 3 different students in 2 different subjects, you can say, okay. And I'm kind of creating a pd.data frame. I'm giving the column names, all those things you know already. And if I'm plotting this, then it will look like this in the beginning. Now see this, guys. In the beginning, this is the how data is scattered, okay. And what we are trying to do, we are trying to capture the direction in which maximum variance of the data is there. So by looking at this, in which direction you think the maximum variance is there, guys? Obviously not in original xy direction maximum variance is there, okay. So we will see how to do that, right, one by one. So I was talking about making data mean centric. So what I'm doing here, mean by column is equal to numpy dot mean marks dot transpose. Now why we are transposing? Every time I say dot t means I'm transposing. So if you want to see what is in marks dot transpose, guys, it is nothing but your transposed data, okay, because I want to take the mean column wise, right? So 326 comes here and 489 comes here, and I want to take the mean, and then I'm scaling the data by subtracting mean by column, okay. So if you see here, I'm printing mean of each column, and my scale data will look little different than the original data. For example, the original data is like 326 489. I take the mean, subtract from all, and if you see here, the numbers of scale data will be changed, okay. This is scaling. Why scaling is needed? Because we will be doing everything on the axis and rotation will happen. So imagine if one of your data is on bigger dimension or axis, not dimension, bigger, I mean to say magnitude, other is on a smaller, it will be a problem. So we are doing this. Next thing what we have to do is, we have done the data mean centric, okay. In step 3, mean centric purpose you would have understood, I'm sure. In step 3, what we have to do is, we started with many features in the data, right? And now we want to understand which features are related to each other more and which features are related to each other less. That is the whole purpose of dimension reduction, right? We want to understand that. So in step 3, we are going to create something known as covariance matrix. If you forgot this concept, or if you want to revise this concept, I'm giving a link here, guys, for one video. You must watch that video. Covariance is nothing but another measure to see how two variables are varying together, okay. So in covariance matrix, what you will see is, if I have to compute covariance matrix between two features A and B, right? So it will be covariance between A and A, covariance between A and B, covariance between B and A again, and covariance between B and B, something like this. So it will give you covariance numbers in different dimensions in a matrix format. Why it is needed? We want to understand relation between different variables, okay. How to do that in Python? Let's come here again, and covariance is nothing but you just go to numpy and say np.cov scale data.transpose, again because we want to do it feature by feature, okay. So this is your covariance matrix. Once you have the covariance matrix, then next step is nothing but what I explained you using eigenvalue and eigenvectors. Now your covariance matrix become this matrix, and what you have to find out is corresponding lambda values and v values. What we want to capture, guys? For that covariance matrix, what is the direction in which my maximum variance is there? And also, what is the magnitude in that direction where the variance is, or how the variance is? So we did all these calculation manually here, just to show you. I showed you, right, matrix subtraction, finding of lambda, all these things. In Python, all these things will happen in one shot. You come here and you say eval means eigenvalues, evac means eigenvectors. You just say eg of covariance matrix. So the first thing that you can see here is your eigenvalue. Second thing that you can, so this is your lambda 1, 8.5 is your lambda 2. The second thing which you can see here, this is your eigenvalue, I'm sorry, eigenvectors. First eigenvector second. So lambda 1, lambda 2, v1, v2 you are having here. Okay. So once you have the lambda 1, lambda 2 and v1 and v2, then what you know is where your covariance matrix direction is and what is the amount of magnitude. But you do not want to work on the lambdas and v's only. You want to project your original data to that axis. For example, let's say there are two vectors in these two directions. Your spread of data or variance is maximum. What you want to do is you want to move your original data to that scale. Okay, so your original data here in this case is this, right? 3, 2, 6 or 4, 8, 9, or even if you take your scale data, right, that is your scale data which I showed you here. Okay, this needs to move to the new axis. New axis means new vectors. New vectors means I will come here and tell, hey, can you project my data to the new axis? So how I do that? I just go and say eigenvector transpose, because that vector is there, right? v1, v2 I'm talking about, and take the dot product with scaled data transpose. Okay, so what I'm doing here, guys, I'm kind of projecting original data, project original data to new axis, project original data to new axis. Okay, and after you create this, then you find in step 4, then you find lambda 1, lambda 2. Okay, find eigenvalues and eigenvectors, that is lambda 1, lambda 2, v1, v2, and this is your step 5. Once you find your lambda 1, lambda 2, v1, v2, then you project your original data to the new axis, because you have found the direction of the maximum variance. Now you do not want to use the old axis, because you want to use the new axis where you want to project your new data and use that, because you want to use limited number of vectors or principal components, right? So it will give you, once I run this, it gives you these values, and what I'm highlighting here is nothing but your principal components. Okay, and in this line, what I'm doing here, I'm importing from Sklearn decomposition import PCA. I'm running the same thing on marks, original marks, not scaled or anything. Okay, and if you compare the results, guys, you will see that the numbers look absolutely same. For example, the vectors are swapped, so don't bother about that. Don't bother about the signs also, just see the magnitude. Okay, 2.9154, this is the main one. Here, this is the main one. Okay, and here another vector. Let me run this again. Did I miss any step in between? Okay, yeah, this is your 16 zeros. So this does not matter, guys. E minus 16 means 16 zeros. This is a very small number, and we don't bother about this. This is 1.11 and this is 6.86. Very small, 16 zeros. Okay, main ones are 2.91 because there are no much zeros, and minus 2.91, no much zeros. Okay, let us compare the second principal component. Second principal component, minus 9.71, E minus 1, minus 0.1, 1.94, 1.94, 9.71, 9.71, 0.1. If you leave some decimal margins, which is after so many decimals, right? Exactly same results, guys, just the lambdas are swapped, which means it is considering this vector as the first vector, manual calculation considering other vector as the first vector. So this is how you compute PCA by manual process, and the result is same as your Sklearn PCA. Okay, one more time, what are the steps? First of all, you have to compute you have to define data, make your data mean centered, find the covariance matrix, find your eigenvalues and eigenvectors like the way I explained, project your original data to the new vector direction. Okay, how you do that? You multiply with the scale data with these vectors. Okay, now few important things here, guys. So explained variance tells you how much is the in your data, how much variance is explained by first principal component and how much variance is explained by second principal component. In this case, 75% variance is explained by first principal component, 25% by second principal component. Okay, and if you want to see this in a tabular form, I have put it like this. So PC1 looks like this and PC2 looks like this. So we started from original variables here, guys. Physics, maths, these are the marks. But now physics and maths is not in the picture. Physics and maths are converted to your principal components, and the principal components are looking like this. Okay. Now, one important concept for principal component is loading, guys. So I will tell you what is loading. Loading is like how much your each principal components weight from your original variable. So you remember in the beginning I told you this is a linear combination of your individual variables, principal components basically. Maybe I forgot to tell you in the beginning. So PC1, if you ask me what is principal component 1 and principal component 2, right? So your PC1 is alpha 1 feature 1 plus alpha 2 feature 2 and so on and so forth. Okay. So what your loading tells you here is physics multiplied by minus 0.51 plus maths multiplied by minus 0.85 is your PC1. Okay. Similarly for PC2. So your principal components are nothing but linear combination of your original features with some weights. Okay. How can you convert your principal component to original variable? You have to use something known as inverse transform, PCA inverse transform. So if you can see here, I'm able to generate the same record that is there in my original data marks. In this case, I took a simple data to explain you guys, but if you run it on a bigger data, obviously few initial principal components will be able to explain 100% of your data variance. Here you can see 100% by these two. If you run on 100 features, maybe first 5-6 will be able to explain, let's say 90%. So you take those first 5-6 and do the work. Okay. Now what we are left with, guys, let me go ahead to the note one more time. Steps to calculate, we compared result with Sklearn and some summary, right? So when should we use PCA and when we should not use PCA? So as you could see, guys, the originality of the variables has gone, which means you cannot use the original variables, or you cannot explain to someone what happened to your original variables. In those cases, PCA is not preferred, but PCA is a very well-known feature reduction technique and very trusted also, because everything under PCA is a mathematical concept. Okay. So what all we learned, guys? We learned mathematics, refresh, eigenvalue, eigenvectors. We calculated manually, compared with Sklearn, and we saw some summary. Please press the subscribe button if you like this video, guys. Please give me a thumbs up if you like this video, and please drop all your questions in the comment section. I will see you all in the next video, guys. Till then, wherever you are, stay safe and take care.